the theory classes for section 2, and the only thing that we've got left to do is Schmidt decomposition. And this is important as it's going to give us a measure of entanglement. I'm going to start with an example. So here's an example. If I say, look at this state. Then you see, maybe because of symmetrical things here, that this is, we could have written as the tensor of two particles. So what we've really done here is we have one particle in this superposition, and we like put it together with this particle in the second system. Okay, so we really just put two together. So there's no, if you like, entanglement in this state between the two systems. The two systems being system 1 and system 2. It's simply this. So this could be, this is some superposition of qubits on the first system and some superposition of qubits on the second. Whereas, if I take a Bell state, let's call it phi, this state cannot be written, well, let's use decomposed. Into, let's say, phi 1, phi 2. Yeah, phi 1 would be a superposition of qubits on the first system and the second one. Okay, so this is more or less like what we want to kind of formalize this idea, and that's what the Schmidt decomposition allows us to do. So the idea is the following. So just seeing if I've got enough space to write it at the bottom. I think so. So here's the theorem. And we will see these two, well, this and its sister, which is purification, which is kind of not really the inverse, but anyway, coming up various times later in the course. So this is kind of important. So let's suppose phi is a state in a composite system A, B. So all I mean here is this is some amount of particles, and this is another. So we have cardinality of A particles and then cardinality of B particles. Okay, so this is just a composite system. Let's see. So another, i.e., phi is a vector in qubits, tensor, and then cardinality of A plus cardinality of B. Right. So this here we have the A and B will just be 1. Okay. So we just had system 1, system 2. So then there exists orthonormal bases. What do I call them? IAIB. And I'm going to use this terrible notation again. I mean, it's not so much the notation. So recall that when I put this, I don't mean the singleton set. I automatically mean that I runs through some index set, which corresponds, which has size the dimension of the system A. The dimension of the system A is 2. Is 2 raised to the power of the size of A. Okay, we'll come back to that in a minute. Anyway, so there is this orthonormal basis IA and IB such that I just put real positive here. Okay.
Wait, the sum, like the index is I, like do they run over like both pairs? Like all like the base of A would be like 1A, 2A, 3A, and for B it's the same. Like does the sum go through every pair of elements from the first basis and the second basis, or just 1A times 1B, 2A times 2B?
Yeah, so okay, so this sum here would be, okay, this would go from 1 to 2 to the minimum of AB.
Really? Wait. Okay, so then it's not like a dual sum. Like it's.
Well, it is the old sum, but maybe just take the lambdas to be 0 after the minimum. After that.
Why this 2 to the minimum?
Well,
like we don't have that.
Because we're going to run out. If let's say A is smaller than B.
Oh yeah, we have yeah.
I mean, they're both running through the same thing. So when we get to the minimum, we run out of basis vectors for the other one.
Yeah. Right. So there are some vectors of B that will not be used.
Exactly.
Yeah. Right.
Is that okay, Adrian?
So wait, I still don't get it, all of it. Like does every element from the basis A multiplied by just one guy from basis B, or with all of them?
No, one guy. So okay, let's have a look at this. So here, this would be IA. So this basis IA, this would be 0 on the first system, 1 on the second system, and IB also. And then you go through the sum 1 over root 2, 0, 0, plus 1 over root 2, 1, 1.
Okay. And then here.
Here, this would simply be IA would be 1 over root 2 that's a curly bracket, 0 plus 1, and then something that's going to be orthonormal to that. So 1 over root 2, 0 minus 1. It doesn't matter here because it's not going to be in the sum anyway. But just so that it's got orthonormal bases, and IB is going to be, oh, this is a plus. This should be a plus, yeah? You didn't spot this mistake, huh? Because they're all pluses here. So this was a plus. And IB is the same. Well, maybe you did spot it, you just didn't tell me. Okay, so here, the sum has just got length 1. Yeah, so I is 1, which is really 0. It's just this tens to this. And then you stop. Adrian, you haven't got your microphone on.
Oh yeah, that is.
I just can't hear you.
Yeah, that's my bad. No, yeah. So then there's always, like, it says that there's always a way to do it like 1-to-1. I mean, from like in pairs, from like unique pairs from A to B and from A and B. Okay.
Yeah.
Okay,
And of course, if the dimensions are different, then you run out of vectors.
Yeah, for one of them, so the other is just okay. There's no pair. Okay. Perfect.
Okay.
Then the lambdas can be 0, right?
Then the lambdas can be what?
0, because you said that is real positive.
Oh, if I say it's all the way up to the 2, yeah, then I have to. Yeah, because before I was just thinking.
And then it's not important that the lambdas are positive, in the sense that you can change the sign of one vector in the basis and it will be orthonormal, and then you can change the lambda to minus lambda. Like it's the same.
Yeah. That's true. That's true, but yeah, so. Yeah, the fact that they're positive. I think, well, actually what I want to do here is put this back to being positive, which is fine, and just say this is at most. Okay? Because what we will be particularly interested in is the length of this sum, how many terms this sum has.
Okay.
Okay? But I guess you're right, yeah, I mean, they wouldn't necessarily have to be positive, but if you have it negative, then you can make it positive just by putting the sum into the basis.
Yeah, okay, the important thing is the non-zero ones.
Exactly. Okay. So now we're going to see all our hard work from Tuesday paying off. Now, I am going to cheat. I am going to assume that A and B have the same size, but I have done the case A is not equal to B, and that will be exercise 8. Okay, so somebody has to go through this proof very carefully and work out how to make it work when A is not equal to B. So we start off just by simply choosing any old orthonormal basis. Oops. for the A and B system. Okay, so just to recap, you know, if A had 3 qubits, this would be running through the binary strings of length 3. Yeah? And this would be running through the binary strings of length size of B. Yeah. Right, then now we have a basis for the system. So this phi is going to be equal to, I wrote down A, and I guess it's okay if we, let's use the full N, because otherwise. So
should we put the sub A and sub B, like differentiate which is which? Like they're, I mean, I guess they can be the same, but it's like if you substitute J and K for numbers, you can't tell which is the basis of A and which is the basis of B anymore. Or how does that?
How do you mean? You can tell just before this comes first and this comes second.
Yeah, but like the expression is equal if you like flip them around. Like you can only tell which one is which by how we write them in the sum. Like if you actually like substituted J and K for numbers, you wouldn't.
You sometimes we will use numbers instead of the binary strings.
I mean, no, like if you put the binary strings, like they don't like the notation doesn't differentiate between basis of A and basis of B. Like that's what I'm asking. Like before we put like you put IA and IB, and here you just put J and K.
Yeah. Okay, see your point. Yeah. Do you mind, or do you want me to put JAKB?
I mean, I'd rather it be that, but like if you think it doesn't matter, or like
I think, you know, I mean, respectively.
but like
the point being that I wanted to stress that this is just taking I as one, the first ones, the second ones, and the third ones.
what do you mean the first one, the second one, and the?
I mean, this is the first element in the basis IA. So when I is 1, this is 1A, 1B.
Oh, okay, yeah, okay.
Yeah. And then it's 2A, 2B, 3A, 3B.
Yeah, okay. And here,
Whereas here, it's just running through the whole things.
Right, but like it's just J and like here the I's were the same for the one for A and here for B, and here they're already J and K, which can be different. Like my question is, why are we doing J sub A and K sub B? Like why are we doing J sub A and K sub B? Like what changed?
That's fine. Do you want me to do that? Okay.
It's not a bother.
Okay.
Yeah. Okay.
That I'll do, but I can't make them the same, and that's the whole point, isn't it? Yeah. Okay.
I mean, you can make them the same, yeah, but like in general, you would differentiate.
Yeah. Okay. Yeah, you're right. It looks neater now. Yeah. Now it kind of corresponds more to where we're trying to get to. Well, basically, we're trying to diagonalize, right? And that makes a lot of sense. So this here, you see, now we've got a matrix. So we can let M be a matrix. Well, this M is a matrix. It's a square matrix. And by singular value decomposition, okay, so we saw that this M, we could write M as U, D, V. So this implies that mjk is the sum of uji dii vik, where this sum is over I. So if we define IA to be the sum of the UJs, with the JAs, of course, so the sum over J of UJIJA, and now I'm just going to rub off the first bit of the theorem statement. This bit we already know by now. And IB, so okay, or to be like KB, then this psi is nothing more than substituting this and this into there. This should just be dii IA. Okay, so actually what the spectral value, singular value decomposition is almost exactly the same as the Schmidt decomposition. Okay?
Could you apply like SVD to the map directly without going through M, or no?
Yeah, I did think about that. I don't think so. I mean, in a sense, you need to fix a basis, right? You need to fix bases. And I don't think there's a way, because you need to get to a matrix which you can then.
Yeah, but I get that you have to do it that way too. Sort of do with the tools that we've done. But like, it feels like at the end that the J and the K don't even matter anymore. Like you're basically saying that there's that you can have like an SVD like expression for the map.
But it's not a map, is it? It's a state.
Oh, right. Oh, anyway, okay.
I mean, what you're doing,
think about it.
I mean, think about it, a tensor product, when we were children, we think of a tensor product as this kind of like vector space of matrices. So if I start off with a vector in my tensor product, I then go, oh, actually, that's really just a matrix, and then yes, that's all we've done.
I don't follow.
Well, it doesn't matter really. Well, anyway, no, because this is a vector.
Okay.
Okay. So, but a vector, you see, what we're trying to use here is the fact that a vector in a tensor product space, in your kind of like innocent view of a tensor product space, was the space of matrices. So we're kind of gone back to that view. So we go, oh, it's a vector in a tensor product space. Well, really, that's a matrix. That's what we just try to prove. And then we apply a singular value to that matrix. We haven't quite finished, actually, because we have to show that these are orthonormal bases. Okay, so we just show, I'll just show one of them and the other one, please. Clear. And so let's just do one of them. And this is going to be very similar to what we saw before as well, is orthonormal. Since oh dear, my handwriting. I want to go too quickly because I think it's all going to. Oh. Okay, so this the bra of this is then. So I've got to Oh, I've used J there. Let's use L here or something. LA. So this would be the sum over J of U J L bar and then U J I J. Oh no, what am I doing? No. So I always get this wrong. So let's say this LA, that's the sum over something. Let's say M of using this U M L M A. Okay, just substituting here L for I and summing over the M's instead of the J's. And now we can just use the same one for here. So then now we've got it clearly. This is MA. These are just numbers. So we're summing over M and J. So this is just sum of U M L R J I M A J A. But this basis here, this was simply, you see, this is probably why I didn't want to use JA, because now I don't see the difference, Adrian, between the I basis and the J basis. You see?
Yeah, you're right.
Can I get rid of that?
I mean, we could have used a super index then.
Yes, super index. Very good. Okay, let's super index things. Yeah, because we need to know, because this one's our orthonormal basis, and we want to prove that the i's, which we've just defined, are also orthonormal. That's down, that's down, that's up. And so this is up, this is up, and now this is up. And of course, this being an orthonormal basis means that this is just delta Jm. So this is 0 unless m is equal to j. So this is the sum over j of ujl by uji. And that's just multiplying u by its transpose. So this would just be delta il. And that's since U Hermitian U is the identity. Yeah, subscripts and superscripts, very good. Okay, so let's have a look at another example. Well, I don't know, that's a pretty trivial example. Don't seem to have a good example here. Anyway, well, you can think of one yourself and just try and. It's good to play with. Just have a try and calculate exactly a Schmidt decomposition for some state. So the number of let's say non-zero, but we kind of define them as non-zero. Is the Schmidt number of so this defines the Schmidt number of this state, and of course that's with respect to the systems A, B. Because if you split up the system in a different sense, so if you had a 3-particle system and you took the first and the third particle with the second particle as the B system, or the first and second particle for the A and the B being the third system, then you can get different Schmidt numbers. And that is one of the exercises. I can't remember which one now. Exercise 9. Okay, so let's say C exercise 9. Because in Nielsen and Chuang, they don't really specify this, but it seems like, I think it's clear that it depends on the systems A and B. They just say the Schmidt number of the state, but the state just belongs to some Hilbert space on n particles, so it definitely depends on which systems you're splitting up over. Now, does this lambda, the Schmidt number, depend on maybe these, well, I've got them off now, these bases JA and KB that we chose at the beginning. So let's just notice that that's not the case. Okay, so if we changed the basis JA, this has the effect. Okay, so this simply just changes the basis here. So this just goes from one orthonormal basis to another orthonormal basis. It is stuck in, it gets stuck into here, right? So it just comes in here. So it doesn't change anything here for the DIIs. Oh, did I say that DIIs are then the lambda i's? Yeah. So these are lambda i's. And of course, having observed that we could have changed well, that was the only other choice we made along the way, was changing the basis. So then what happens is you see that the number of non-zero lambda i's we get, so the Schmidt decomposition is equal to the rank of this matrix M. So the Schmidt number is equal to the rank of M. And these DIIs also go under the change of basis, of course. So the lambda i's also fixed. And now you see why. Now you see why you couldn't go beyond. You didn't need to go beyond the dimension of the Hilbert space of one of the systems, yeah, because you simply couldn't, you wouldn't be able to get the matrix larger than the 2 to the A or 2 to the B, whichever is smaller. Okay. Right, so yeah, I did try to think of some other good examples. The problem is thinking of just making up examples, like, okay, I'll just write this one down. Think about what we had to do to, if we need to apply the singular value decomposition, we need to apply the polar decomposition. And to do the polar decomposition, we had to do J was A Hermitian A, and then diagonalize J. So that's where the work is. So at some point you have to diagonalize a matrix, then go all the way back through it. Once you diagonalize it, it's not so much work. But so if you just write down a random state, you can then fix your bases. Well, just use the computational basis. You then get your matrix M, and then you say, okay, let me find my UDV. But to find the U, you remember, you had to find to do that, to do the singular value decomposition, we had to do the left polar decomposition, and to do the left polar decomposition, we had to find the eigenvalues and eigenvectors of M Hermitian M, and then take the square root. So it's a long and torturous process. And then if you try to make one that's too trivial, then it's obviously too trivial because you made it up already. Yeah? And it's very difficult to find the intermediate. Okay, are there any more questions about the Schmidt decomposition? So there's quite a few exercises about that, so we will work through those on Tuesday. Okay, so in exercise 9, I wrote down a state on a 3-qubit quantum system, and we have to calculate its Schmidt number for 2 ways. So whoever got that question, you don't actually have to diagonalize any matrices. You can do that question without diagonalizing. It's because I chose it very nicely. But if you chose just a kind of random state, then you would have to. Okay, so what I should say, so the Schmidt number gives us a measure, and this is the important bit of the entanglement. Of phi between the systems with respect to the systems. AP, of course. Okay, so if you think back to the Bell state, so the first example we had, this one, this had Schmidt number 2, which was the maximums it could have, so it's a maximally entangled state. Whereas the other one has Schmidt number 1, and that's because it wasn't entangled at all, because we could split it up and write it this tensor this, which is just the same as having this particle and then putting it together with this particle, putting them next to each other. No entanglement. Okay? And now you can imagine, well, you've got a 100 qubit system, here's the state, I want to split it up. What's the entanglement between the first 50 particles and the next 50 particles? Now you know how to calculate it. Okay? And what's going to be important for us is when to use the power of the qubits in a quantum computer, what you need to do is really use entanglement. Okay? Entanglement is absolutely fundamental, because even though you can superpose each qubit, that's not going to give you any more power, really, because when you measure it, let's say in the computational basis, that's all we've done at the moment. When you measure it, you only get a 0, 1 anyway. You see, there's no other information there. You might as well just used a probabilistic classical computer. Okay? Whereas with entanglement, then you're really going to use all the power you've got. You've got your 2 to the n states. Okay? And all these entanglement in between, and yeah, so that's where. So this is what we need to use to, so not only in our quantum computing, but also when we get to entropy and to quantum error correction, this will be of fundamental importance. Right. Any questions? I can only see Adrian, he doesn't look very happy. So I hope the rest of you look a bit happier. Sorry, Adrian.
No questions, no questions.
Thank you for being there. I can see you everywhere. Right. So now we can start officially going through the postulates of quantum mechanics. Now, a lot of this will have already hopefully now look very familiar, but I don't see any reason not to write it down formally. And at the end of this section, of section 3, we will try and go through some, well, I won't actually do the experiment, but some experimental results indicating that this is the correct way to look at our universe. So this is now section 3.1, the state space. Oops. This will be postulate 1, and there are 4 in all. Associated to a closed quantum system. It's a complex length of space. With a and the system is completely described by a unit vector in this space. Okay, so that's what we've been using all along. We also saw, alternatively, so we can describe the system by a matrix or an operator, let's say operator, acts on this space. And this is called density operator. And is positive with one. and this allows us to describe an ensemble of states So this describes the system with probability Pi. And it occurred to me after we saw this before, so instead of just looking at the state as a vector, we look at it as a most of the time look at it as a rank 1 matrix, because that then allows us to describe ensemble states, and we'll see why very shortly why that's important. So and this is simply saying we are in state psi I with probability Pi. This then no longer needs to be a rank 1 matrix. This should be not any old matrix, but a matrix which is positive and has trace 1. So yeah, the trace is 1 because the trace is linear. So and the trace of all these rank 1 matrices is 1. And then when we sum up the probabilities, we get 1. That we saw before. What I forgot to show, I think, was that it's positive. Observe, we'll do that now. Observe that.
What do you mean with, like, we can describe the state completely with 1 unit vector, and then sort of we bring up the ensemble? Like, how does that, I can't reconcile that. Like, we can describe it as just 1, and then we say that we need several. Like, I don't get that part.
Well, only that if we know if the system is always in some state, right? Psi, which we can also look at the rank 1 vector psi.
Okay.
No problem. Here I'm just saying, well, maybe we don't know what the state is, but we can decide a set of possible states.
Okay.
Okay, so it's just that maybe, yeah, the system is described by a set, but maybe we don't know what it is. Yeah? Maybe we're not sure. And I just want to show this as positive, so that shouldn't be too hard. So this is the sum I, Pi, phi. And of course, this is this should be up here. This got to be very careful not to mix up my p's and my rows. This is, of course, this conjugated. So all I'm doing here is summing real positive numbers. Okay? So this is positive. So the definition of positive is this is always positive. This is always a positive real number. Yeah, so for example, let's be radical and put a complex number there. We always have describes a state. Well, let's change it first. Okay, so this will describe, say, a three-particle system. Or three cubes. Maybe better to say three cubes. And we say we call the coefficients. The coefficients are sometimes called amplitudes. I probably won't use that. I'm just telling you these things just in case you read them elsewhere. So, so they might say the amplitude, in this state, the amplitude of 0, 0, y is 1 over root 2. There's something curious here. So let's say, another example. Let's use the matrix thing just because then you'll see the maybe a little bit there. So the 0 and 1 will be actually, you know what, let's not, because that's actually going to be more difficult for me to work out. I think it's easier actually if you just, because you've got it here, so it's going to be, you just write it down. I'm just worried about getting the signs wrong around, so, but if I do it this way. Let's do it in the order that you would see it in the matrix. Read it in the matrix. So this would be this matrix, and the trace of this. So in matrix form is so 0, 0, 0, 1 here. So it would be 1/2, 1 minus I, 1. And this in matrix form is kind of easy to do. The square of the matrix. So I just want to work out what's the trace of this matrix, of this operator squared. And if I look at the matrix, then all I need to do is square this and add the terms on the diagonal. So if I'm squaring this, I get 1 plus 1, which is 2. So I get a 1. Let's do it like this. It's the trace of, I've got 1 plus 1 is 2, divided by 4 is a half. Something I don't care about, something I don't care about. Minus I squared is 1 plus 1 is 2, divided by 4 is a half. So I get that the trace of this squared is equal to 1. Okay? And now let's think, well, maybe we don't know it's in this state. Maybe we're only kind of sure, maybe it's only in this state with probability 2/3, and maybe it's in the state 0 with probability 1/3. System. And now I use my density matrix to allow me to this. So this would be represented by rho, which would be 2/3 of the matrix here. Plus 1/3, 0, 0, which is this matrix. And now we could calculate again the trace of rho squared for this one. And what you find is, so I just need to calculate what this first and this one will be. So it'll be 2/3 plus, 4/9 plus 1/9. So it'll be 5/9 plus 1/9 and 1/9, 2/9. And the reason that I did all this was in exercise 2.4, from sheet 2, even though we're already in 3, but we did it out of order. So it gave me a chance to show you an example before somebody has to prove that and now I'm going to do something which is just seemingly strange thing. I'm going to say the density operator is pure, i.e., this is equal to this for some psi. Okay, so we better get used to the language because it's used all the time. Okay, so they call it a pure state, even though it's a density operator. This is the pure state, but this is the density operator corresponding to the pure state. But unfortunately, a lot of the time, this just becomes density operator. The density operator is synonymous with the state. And then when it's just got rank 1, they say it's a pure state, when it's really just representing a concrete state. Not my fault. Okay, so that's just the way these things are done. So that we saw in these examples here, we took a pure state, we calculated the trace of the density operator squared, it turned out to be 1, and here it's less than 1. Okay, so in fact, it will be trace of this is less than or equal to 1 with equality if and only if, with equality if and only if the state is pure.
I have a question because you are saying that we can represent the state with the density operator.
Yes.
But we saw that the same density operator can be given by two different states. So aren't we like losing information here?
Yeah. Yeah, but it will turn, yes, I see your point. It will turn out that any information that we can get out of the system by measurements is contained in the density operator. Okay, so I'm just trying to think of how was that, because I don't have the notes for that bit now, I think.
Yeah,
let me have a look at that example. Yeah, I remember that we did that after. Oh no, I do have this here.
Yeah, if you do like a change of basis with a unitary matrix, it will remain the same.
Yes, because that was describing an ensemble of states, right? So so in the example, we had two different ensembles of states with the same density operator.
Yeah.
Okay, so what I'm saying is, yeah, in that case, you will not be able to differentiate between those two ensembles.
Okay.
So, yeah, in the case of this, then this is simply a rank 1 matrix. You can recover your psi. It's a definite state. It's a pure state. In the case where you don't have it pure, yeah, not to be confused with superposition, right? Two different things. In the case when you have an ensemble of states, then this describes, the density operator describes the ensemble of states, but not a unique, it's not unique. You can't go back the other way. However, all the information you can get out of the system is in the density operator, which is not obvious at the moment, okay?
Yeah.
Thank you. Good question. Right. Oof. Evolution of closed, so that's postulate 1. I think this is a good exercise to go because we haven't already seen all of these, but now we're doing it a little bit more detail. So what you're really saying with that exercise is that the trace of the square of a rank 1 matrix, which has trace 1, has trace 1. Okay, so if a matrix has trace 1 and has rank 1, and you square it, the trace is still 1, and that's if and only if. Yeah, that's basically what you have to prove. So. I guess we want closed there, yeah? So closed. The reason I keep writing closed, yeah, because the environment, as we will see, does affect our quantum system. So, but we will come to that later. Postulate 2. The evolution of a closed quantum system is described evolution. By unitary. And we've already seen many examples of unitary transformations. Examples, very important ones for us will be the Pauli operators. X, Y, Z. Another important one for us will be the Hadamard, which we've already seen, which as a matrix is 1 over okay, and we recall that h of 0 was plus, which is the perfect superposition, and h of 1 is minus, which is the second problem. Okay, so that's just we're calling the Hadamard. That's just an excuse to, and you can check. Check. It's unitary. So that. Okay. Unfortunately, this H is not the H I'm about to write up. The continuous evolution of a quantum system. The word dictated, given by, is given by, oh, given by Schrodinger's equation, which is this. I guess you've probably seen this before somewhere. So what this is saying is, as time evolves, the state is being changed by this H. This H is not this H, so let's get rid of that so we don't confuse anything. I partly did that just to make sure that you realise that this is not the same H. So that was kind of on purpose. So where this H is the Hamiltonian Schrodinger's system. Now I can get a little bit of physics on you and just have to talk about the energy of the system, and this is part of the energy, and it's the sum of the potential energy and the kinetic energy and all the things that you learned at school in physics, but I'm not going to go too far into that. What I will do is try and solve Schrodinger's equation for you and show that the solution really is a unitary transformation. So I just want to say what it is. I'm just going to do this, and it turned out, and this was discovered experimentally. So this equation was discovered by Schrödinger experimentally, and he had all the data, and I think maybe someone, or at least I like to think that somebody was looking over his shoulder and went, that's multiplication by a Hermitian matrix. So H is a Hermitian operator, which makes you kind of like think that God is really just loves complex linear algebra. I mean, just to put it at such a deep level in our universe. So how do we solve such a differential equation? Well, if you're, I mean, there are different ways. It's rather like, if you don't know what you're doing, you can solve this very quickly. It's rather like painting. It's easy to do when you don't know what you're doing. And you just go, oh, well, this is differentiating, it pretty much stays the same. So it's the exponential, right? So the solution is E. So it's some. So how would you solve this? Don't want to use. Let's use A. This would be CFO. So when you differentiate, the A comes down, which is the same as multiplied by A, and the constants cancel. Okay? So it's the same. So this solution would be here, psi is equal to some constant, we'll call it, well, let's put C, why not? C, e to the h d. And of course, that is actually true, but you need to have defined what's the exponential of a matrix, and we did. We did actually define what the exponential of a matrix is when we did a diagonalization. Okay, so that's a valid solution. So it all works. I will give you another solution in a minute. But let me just finish off. So this C, we have to find out what happened at time 0. So at time t0, let's just put in the initial conditions so that we can work out what C is. This will give us psi 0 is equal to C e to the, and now let's multiply by minus I top and bottom, so it looks a little bit easier. No, actually, maybe that's just going to confuse me. I'll do that later. So this implies that the solution is, and let's put the number first, if you like, e to the operator first. Yeah, because this is really just an operator. E to the h I over h naught. This will be a minus, so it'll be t minus t naught times whatever you start with. Okay? And now I'm just going to put this I at the top. So this will be minus I. So that's the solution to Schrodinger's equation. And it is now exercise number 1.
What exactly is the Hamiltonian? Like, does the system determine the H, or is the H sort of free, or how does it work?
It depends on what your particles are. So let's say you had like electrons going around some nucleus of a certain atom, then that will have a Hamiltonian.
We'll have a what?
So that you could ask, what's the Hamiltonian of electrons going around a silver atom? I don't know. Yeah.
Okay. But then
this will have a certain number of electrons, and there will be some. If you could isolate your silver atom, then you would have an Hamiltonian describing the system. It's all to do with the energies, as we shall see in a minute.
I mean, there's only one way that a certain quantum system can change continuously, like the one that's given by this H. That you can't. Like when you have the discrete system, like you can sort of choose the gate or what do you do to it, but here you can't. Like that's what the part that I don't get. Like that before you could choose the unitary transformation, but now the sort of H is given to you.
Because this is a closed system. Yeah, we're not doing anything to it.
Okay.
Yeah. So, and also when we do something to it, it will change with respect to it will always be a unitary transformation.
Yeah, but
here it's just like, let's say, you have a Hamiltonian describing the system. This is nature changing it.
Okay. So it's how nature would change in nature if it started in a specific initial state. Okay.
Well, this T0 doesn't matter, but so it will be exercise 1 on sheet 3 to prove if H is Hermitian, then U is unitary. Which kind of was an indication that to come up with a Copenhagen interpretation of Schrodinger's equation was that these this unitary transformation was preserving the probabilities, was taking unit vectors to unit vectors, and therefore we should think of these superpositions as probabilities. Okay? Not to mention the fact that when we do the measurements and everything, but we'll get to measurements in a minute. Yeah. So if I was actually teaching this to the engineers, so as not to frighten them with exponential things, with exponentials of matrices, you can also just solve it. I mean, let's just simplify it, just put an A in. So let's just say we had some differential system, differential equation like this, okay? Which is really a system, isn't it? Because these are vectors and this is a matrix. This has a solution. I don't want to use it. So this has a solution, and this is clear, because if you differentiate this, then the lambda comes down, right? This is just a vector, fixed vector. And if you multiply by A, then since this is a eigenvector with eigenvalue lambda, this just gets multiplied by lambda. Okay, so these are, and the reason I'm telling you this is because these are the stationary states. These are the energy. So these are the energy values, and this is the stationary states of your describing your Hamiltonian here. Okay, so it looks like we've got two different solutions because we've got the matrix solution, and then we've got the eigenvector solution. But really, this is just a particular solution. This is not a general solution. Here we've got a whole load of solutions because this has a load of degrees of freedom being the initial state. And here we only have 1 degree of freedom. We can multiply by a constant here. Okay, so it's of course, then you just sum up. If you sum up all the linear combinations of the eigenvectors, you will get then this solution. I.e., you get the solution. So if I do, let's say what they can do it, can't we? Well, assuming all the lambdas are different, okay? Just to simplify notation. I wasn't actually going to do this, but so presumably, if we do this, this should be equal to some constant times e to the a t. Yes. Which would have been the general solution using the exponential. Okay, when we differentiate, the a comes down. Okay. So it looks a bit strange because but think that these are vectors. Here you're going to get like exponential things going on. Here you've got so you get your run from t0, t1, t squared, t cubed, t etc. It's here. Then you're going to get a matrix, but then you get the matrix multiplied by this first thing. So again, we get a vector, which must be this linear combination. Okay, so it's just so you can. Yeah, you can then see that your different values of lambda correspond to physical things within your quantum system, which are the energy states. Energies of the system. Right. Ah, yes. So just to finish this bit. So now let me just go back. So we've determined that u. So we've got this phi goes to u times phi, which implies that if we looked at the matrix, this would go to. Sorry, all the way around. Okay, so that's clear. But this also follows through if this density operator is not just a pure state. So if this is really just the sum of Pi. All of these get transformed by the which we can pull outside. Okay, so it's exactly the same. So the evolution of the density operator is pre and post multiplied. Pre multiplied by the u and post multiplied by the emission conjugate. Okay, still got time to get on to measurements. So now things, up till now, I think we're pretty much, I didn't have to go into Schrodinger's equation. I could have left it just that we'd already seen that the state changes by a unitary transformation because the probabilities, unit vectors have to go to unit vectors because of the probabilities. But now we are going to really expand our idea of what's a measurement. Okay, so I'm going to take this a little bit slowly. So we have some kind of idea of what is the measurement. So all we have is a very general definition. It's just a set of operators, which I'm terribly sorry. I'm going to use this awful notation again. So this is the index set that runs through an index set. And the only condition, I think, index sets, which are the possible outcomes. Which satisfy. I mean, it doesn't matter which way around it goes, but that's I'm surprised with that. This. Okay, so it's just a set of operators, m runs through an index set of possible outcomes which satisfy this, where the probability that m occurs
Are we missing the little m on the second big M?
Yeah. Let's give it a name, PLM. Right, and well, let's leave this. And the system after the M measurement, if M occurs, is basically NM times this. But the problem is with this is that this is not going to be a unit vector because, well, obviously if this was a unit vector, then this probability would be 1. So we have to normalize it, which is dividing by the square root of this probability. So when I first saw this, I was like, what? And I said, why? Why? And my physicist friend of mine said, nobody knows. So no, that's what happens. Okay, you have a set of different measurements, and you measure, and this is what happens. So nobody really knows. Just trying to think if I can think of a good example. So I guess we should look at an example we've already seen. So what does this mean for the measurement in a computational basis? So measurement. So you see really that it's just a generalization of the idea that we already had. If I tell you that, think about if we define M0 as being then this will be exactly what we had before, right? I mean, this is just measuring our qubit. So we get 0 with probability and that, of course, is simply a RA. Okay, so no mystery there. So all we've really done is just taken the kind of measurement in the computational basis, and we could have done it with 2 qubits or 3 qubits, as we did when we did teleportation. We measured the first 2 Alice measured the first 2 qubits, so she would have been measuring in the computational basis, taking 4 m's, the 0000, 0110, 0101, 1010, 1111. Okay, she measures in those 4, and she gets each result with a probability, whatever it will be. And after the system, the thing collapses into this. Okay, so that's exactly the same. It might be worth running through the example of teleportation just to see. Okay, now let's work out exactly what are the measurement operators we use there. So in the computational basis. But this is a much more general thing that we can do. Okay, and one thing that I kind of I'm not sure I'm going to have time today to run you through it. But I worked out an example where you could have. So I hadn't had a false impression in my head that the number of measurement operators is going to be somehow related to the number of qubits we've got, or the dimension. But that's not the case. So I mean, we could have. There's no restriction here on putting 4 different measurement operators on a 1 qubit system. Okay, so maybe for some reason this gives you what you are trying to find out about the system. Okay, so I'll give you an example of that once I've talked a little bit more about the theory. So we'll probably start that on whenever after we've done the exercises. But so this is what happens to the state psi. Of course, I also know what happens to the density operator. Well, that shouldn't be too hard to work out. Oh, I forgot to mention something here. Observe. So we should observe that. So before we go there, so observe. If we sum over n the probabilities, this, of course, is 1. So this implies what we had before as the condition. So the condition is really saying that the sum of probabilities is 1. So in a way, I mean, imagine how general this is, in fact, because you could just take any old operators.
Why does it imply? Oh,
Sorry?
because it has to happen to every vector. Yeah, right. Yeah. I was like, my question was why this does imply, but if this happens in every vector, this should be. Like, I didn't see the implication, but now I do.
Oh, I see. That if this is 1 for every single vector, then it must be low density.
Yeah.
Ah, no. No, that doesn't.
Yeah, you can take a base or something like that, and.
Oh yeah. Then you just take a basis, of course, and it marks out.
Yeah.
Yeah. So you could just take, well, not quite random, but let's say you took, well, we'll see the example later. Actually, that's probably what we'll talk about later. So I just want to see what happens to these density matrices then. So if after the measurement, I'll just, I don't want to get rid of that. So PM was. Now, what is the trace of this matrix? Oops. If we extend this side to an orthonormal basis, then this trace is the sum over this orthonormal basis. I don't know. Of but this is an orthonormal basis whose first element is psi, so all these terms are zero, apart from the first one. So this is simply I wanted to put, sorry, I missed out on my lens. Okay, so what I've proved is in fact that this thing, and you get kind of used to this after a while, that these things you can just move, you can cycle them around even though they're kind of like, well, yeah, they're not square matrices, are they? But anyway, so this is actually equal to the trace of and you have probably worked out why I wanted to do that, because what I've suddenly got here is my density operator for my pure state psi. And this will be exactly the same. So now I want to prove that this is exactly the same. Yeah, I'm just concerned I'm going to run out of time. But anyway, I am going to, even if I do that, I'm also going to run out of time. Yeah, let's just keep going then. So this would be my operator from my density operator from my pure state. So I want to check now that this is actually works for a mixed state. Yeah, actually, I'm not sure if that implies that, does it? I'm a bit worried now. You've got me worried. Surely that just means that it's. I mean, anything that's unitary.
Maybe it's like a movement, like, because it only has to preserve distances.
I think the completeness is the other way around. Yeah, we have the completeness relation so that the probability is sum to 1.
Yeah. That works.
I think that works that way. Yeah? So I think that's what I was trying to show, not the other way. So I got the implication rather the wrong way. Okay, take me back. Rewind. Edit. This is the problem. This is the problem having it all recorded. You record all my mistakes. Yeah. Okay. So amazingly, and this formula will carry over to mixed states. So let's see that. So for mixed states, okay, so now I'm kind of start using the informal language, so for non-ensemble states, I should say. But you kind of think of these as being mixed and pure. And it's good that I use these terms, because if you just open up any book on this, these are the terms they use. Okay, so it's not even a state, right? It's a density operator. But so that's really a density operator of an ensemble of states. Okay, so what would happen to this after our measurement? Well, do I want to do the probability first, or do I? Yeah, so the probability of m given I, okay, well that's just going to be sticking I, so on the subscripts there, there's going to be this. And this, I think, will probably be the last thing I try to do today. And by the law of total probability, by theorem of total probability, then P of m should be the sum over I of P r m given I times Pi. Okay, so I expect you all to know these basic probabilistic things. So now we can work out what P of m is. So P of m should be the sum Pi. And we already proved that this thing is in fact the trace of m bar m. So what I have here is Pi, the trace of m. And I don't think you'll mind if I move this in here. This is trace. Now, using the fact that the trace is additive, this is then equal to the trace of, I'll just move the sum inside. And now I can, yeah, so this is just since we have distributivity for multiplication of matrices, as long as I don't change the order, I can move this sum here, and I'll manage to get back my density operator. And we get exactly the same formula as we had for the pure state. This is the trace M. So this is giving us a very easy way just to get the probability. Now, I'm not going to go, because I don't want to rush the next calculation because it's even more tricky. So I'm going to leave that for next time. What I'm going to show you, I'll tell you what I'm going to show you. I'm going to show you two things at the beginning of the next theoretical class. Firstly, that when we, after the measurement, we saw that for the viewer state, we had m of psi over the probability of m. So we will, so as a density operator, this is then m. Sorry, this is as a density operator, this is this. And unsurprisingly, we will again have m rho n dagger divided by the probability for a non-mixed states, for mixed states as well. Okay, for just general density operators for ensembles of states. Okay, so that's going to give us, we're going to get the same formula coming through. Now, and then we're going to see, what happens if we had a measurement operators, but we didn't actually know, we haven't actually performed the measurement yet. We don't know what the system is going to be. And we're going to see that what happens is, even if you start in a pure state, psi, what you get, of course, is an ensemble of states. Okay, so that is kind of where you see the density operator coming from in a very natural way. It's like, oh, it's the result of a measurement where I haven't actually done the measurement yet, or nobody's told me the result. Okay, so that's what we're going to see next time. And then I'm going to give you some more examples of measurements and stuff. And we have lots of other bits still to do in this section. But so that's a good start. On Tuesday, then, I would like to go through the exercises of exercise sheet 2. Please email me over the weekend if you have any problems. I will try and answer. Okay, so I think we'll leave it there for today. It's quite a lot. And yeah, I'll see you all on Tuesday. Okay, bye.
See you.
Goodbye.
I can't stop it.